Thank you for the invitation. My name is Steven Gryze. I work for the Climate Corporation, and I'm a senior staff data scientist there. I'm a soil scientist by training. I also have a degree in statistics. At the Climate Corporation, I basically function as a consultant, and I help our science team to scale up their models in terms of data input pipeline or compute. We are heavy users of Domino and very happy customers. We have about 150 data scientists on Domino, and we're building all sorts of cool models and tools for our users. We basically, in general, build a set of digital tools that help farmers understand their operation better and also make better management decisions. And we do that by focusing on 4 areas. The first area is data connectivity. We have a device called the FieldView Drive that you see there, and that device you can plug into your farm equipment. It's going to capture all the measurements that are done by the equipment, and these days everything is GPS enabled, so everything is geotagged. It's going to stream it over Bluetooth to a phone or a tablet, and then upload it to our cloud. We have an iPad app there in the top right. That tablet app you would put in your combine, and while you're in the field, it will show you what's going on right there in that location. And so, for example, if you're harvesting and it's 2019, you can see exactly in 2018 what happened in that spot. And that may, as a farmer, give you some ideas around what to do next year. Maybe that's a spot that's a little bit lower in fertility. Maybe there's an issue there with elevation. So that's very useful. We also have a suite of analysis tools, and that's typical post-planting, post-harvesting analysis. Most farmers are born experimenters. They're going to put a strip of a different competitor seed in there. Maybe they're going to do a little bit more fertilizer in one field than another field. And with the analysis suite of tools, we can give growers the ability to really look at what is the impact of a certain fertilization strategy across your operation. And that helps them also with planning for the year after. And then finally, we also do recommendations, mostly of seed hybrids, as well as fertilizer. And that's basically a Netflix type of problem for a given soil type, for a given weather scenario, and given what you've done in the past, what sort of seeds can we recommend for you that will be successful on your field? So the data science opportunities that we have at the Climate Corporation are, at least at a more pragmatic level, just creating insights and recommendations for our growers. And so we're in the business of precision agriculture, and the whole idea there is that we can use fewer inputs and put those inputs, whether it's pesticides, crop protection, fertilizer, or seeds, to better use. So it should work better for the environment as well as the pocketbook of the farmer. So that's really exciting. That's at least the reason that I am interested in agricultural technology, and that's a reason why that's one of my passions. But at a more fundamental level, what we're really after is to solve what we call the yield equation, which is this elusive relationship between genetics, so the consistency in terms of the genome of the seed, the environment, which is weather and soil type, and then also management practices and all the interactions thereof. And the reason why this is so difficult is really a matter of combinatorics. There are thousands of soil types that each interact differently with the weather, and that will also have different impacts depending on the genetics. So there's just too many options for us to explore. Traditionally, this has been done by process-based models, but they're not super performant. And so data science really has an opportunity here to completely revolutionize actions and decisions made by farmers. So what we're trying to do is, if you see a yield map, and this is a real field, is trying to understand why is it that we have these red spots of lower yield there. Is that because maybe there's a slope and it was a dry year and there was more rainfall that was running off that area? Or is that a lower fertile area in the soil? Was there something wrong with your fertilizer? Maybe there was a nozzle clogged or so, and the fertilizer wasn't really well spread there. We don't know yet. But data science is a great tool, is a great approach at least, to start thinking about the diagnostics, about the causality of differences in yield in a field. In the next few slides, I'll basically go over the data science practice at the Climate Corporation. I'll talk a little bit about the data diversity that we're seeing and how we're storing and ingesting that data. I'll talk about the analytics platform, and I'll also explain how we use Domino. And then I'll talk a little bit about model development and model deployment. So first up, data diversity. So working in data science within the broader agricultural area really means dealing with a huge diversity of different data types on a daily basis. For example, we use satellite data very extensively, and you can think of that as time series of rasters. So that's 4-dimensional. We have latitude, longitude, number of spectral bands, as well as time. We also get a lot of management data from machines that are running on the field. So whether it's tilling or harvesting or fertilizer spreading, spreading of crop production products, all of that data is streamed back to our systems. And those are also basically time series of rasters. So that's quite voluminous, that bucket of data. In addition to just time series of rasters, we also have static rasters. So that's soil type and elevation that mostly is public. So we can either use USDA, for example, to download the data, or other public organizations to get, for example, elevation data. We use hyperlocal weather. That's time series. It's not spatial for us because we work at the level of an agricultural field, and the weather doesn't really change across a field. We also use sensor data. Sometimes farmers use sensors, usually spectral sensors, to get a sense of what's going on in a field over time. We work a lot with vector data and point locations. Vector data just to get the activity boundaries. And for point locations, things like soil sample campaigns are ingested by our systems. And then finally, our division, the Climate Corporation, is about 500 people, but we eventually roll up into Bayer. So we're acquired by Bayer a few years ago. And with that comes a lot of enterprise data. So we have a data set of genetic information of seed hybrids. We also run our own system of research farms where we do on-farm experiments. And that data is also used again to help us create better recommendations for our customers. We spend quite a bit of time and effort to figure out how to best represent that data for our data scientists and how to extract value out of that. And what we basically came up with is that we have a set of production data ingest systems that are fairly siloed. And they're the systems that collect the raw data directly. And so they will be either collecting streaming data coming from farm equipment that's running in the field in a live way, or they would be connecting to government databases to get soil data, weather services, third parties, and then obviously we'll have a lot of internal data in terms of our users, metadata around users, how they use the different applications, and so on. That data is siloed, so these systems don't really talk to each other, and the data is also raw. And that means that the data may be in different projection systems, it may be gridded differently. There's a very low level of data quality assessment that is going on at this point. And so that's not really very useful for data science. And that's why we re-ingest that data into our warehouse specifically for data science. And at that point, we're going to normalize the data. We're going to try and really come up with a standardized grid. We're going to try and put everything in the same projection system. We're going to deduplicate the data. We're going to, at least at some point, do some cleaning or data quality flagging, and then also add some derived data layers. The deduplication is huge. That's a huge sort of lesson learned, where the reality is that a single field may be managed by multiple stakeholders. Even though there's a single farmer and there's a single leaseholder, it may be that fertility is outsourced to a different firm, or they may be using a combine from a neighbor, they may be using another piece of equipment from the co-op. And so these pieces of equipment all will stream data potentially to different accounts. And the only thing that they have in common is the spatial context. So we need to do quite a bit of spatial computation to make sure that for the single spatial unit, we have all the data that's happening on the field, and we can create a calendar basically of what's happening over the year. So that's our data warehouse. That's mostly in Spark. It's mostly Parquet files. And that's done by a separate team, the data analytics team. And they're running the ETL jobs basically in Airflow in a very systematic engineering approach. Our data scientists work within Domino and interact with that warehouse, which is terabytes, if not petabytes, of data from within Domino. We use a single Spark cluster, a single EMR cluster that we share across 150 data scientists. And that actually works quite well for us. And these data scientists can do the typical aggregations and group bys that you would expect. Things like, give me the proportion of a specific brand of seed by county, or where are the fields located that have delayed their planting because of adverse weather conditions. And so this type of insights we can use for the enterprise, or we can also write blog posts around that we can send back to our users and help them understand really what's going on in their field and put it into context of agriculture in general. We also use Spark on Domino to prepare data for modeling, and that's also really been a super successful approach, where our data scientists write PySpark jobs to extract the data that they need and put it in a format that they can then put into either scikit-learn or TensorFlow or so for further modeling. Most of our modeling jobs we do on Domino, and that works very well for sort of the small to medium scale modeling jobs. Some of the models that we work with, especially models that are around remote sensing, are just huge. And I'll give a case study around that later on. And so to be able to manage and train on a very large data set, we're talking about terabytes of data, we have used SageMaker. And that's been a really great success story for us. So we're using SageMaker from within Domino because we like Domino. We want to work in Domino. Domino gives us the ability to share data, the ability to run experiments, the ability to make sure that we keep track of results, it's reproducible, and so on. All the things that you've heard before, we still want to keep those. But the aspect of SageMaker that we use is the ability to spin up a cluster of 50 nodes that have all dependencies for deep learning installed, and that also can detect which node is the parameter server, how do these nodes communicate with each other for distributed deep learning, all of that in one click. And so that's been really, really amazing for us. So we're not using the sort of pre-canned models that Dan was mentioning in the beginning. We are using custom models in TensorFlow on SageMaker from within Domino. With this approach, if our data scientists use best practices, there's a seamless transition. You start developing your model on the Domino instance. So you basically create your TensorFlow model on the Domino instance, and maybe you train it with 50 examples or 50 observations. You make sure it runs. And when you're ready to deploy really to a bigger cluster, it's just a matter of a switch in one of the method calls. SageMaker also keeps a history of logs, a history of training jobs, so that makes it also very easy to reproduce modeling efforts that have been going on in the past. The other thing that I want to mention in this context is that I feel that Domino also blurs the team boundaries because it's such a great tool for collaboration. A data scientist may run into an issue and they may very easily just send the link of their Domino project to an engineer who can log into that instance and can see what's going on, help them, and then make sure that they can move on again. And so that method of working is much more in the hybrid approach when James was presenting his first presentation than sort of the centralized approach. And that has been really successful for us. Once a model is production ready, or is at least considered to be put in production, we have a separate set of tools that we call the model platform that's mostly built in-house, where the models are being put into production. And so the model platform consists of many components, but I'm just mentioning 4 here. There's a model repository, an area where we can put models and also metadata, so the models become discoverable. We have also the models can be versioned, so we can potentially run multiple versions of the same model, or we can have a lineage of versions, all leading to the current version in production. There's a separate service that is doing the runtime, so you can pick up a model from the repository, detect what type of model it is, then select the right runtime and create automatically an API or an endpoint for that model. I've talked mostly about machine learning and deep learning models, but we have a whole suite of process-based models that have a Spark backend as a runtime, and we have also a lot of operation research models. Those are optimization type of models that we use to optimize seed portfolios, and those have a Cplex, if you're familiar with that technology, backend. Once that model is running, there's separate components that are going to inspect the model while it's running, so we can do some monitoring on it and potentially detect things like feature skew, input distribution skew, and then finally we also keep track of model history. There's a lot happening in this space right now. A lot of these tools that I think are for many companies still built in-house and maybe built in-house in an inferior way are being open sourced by bigger companies. And I am personally a strong believer in TensorFlow Extended, which has a lot of model monitoring and model history aspects that are really very beautiful and very well performant for deep learning. So I'll end just the more general section before I dive into the case study with some lessons learned. The first lesson is another variation on the theme of the centralized versus decentralized and hybrid approach. Full stack innovation teams are really the most effective. If you have a team, even at the beginning of your innovation, where there's somebody that's more of a model practitioner and somebody that's more of a data engineer and someone that's more of a machine learning engineer, all working together from the get-go, you're really going to see fast results, because the right decisions will be made on how to structure the input data so that the data can also work when it's, instead of 5,000 observations, 5 million observations. And so we won't have to rewrite that model in a different language or a different framework just because we're increasing the scale. And the second lesson that we've learned is Domino is great. It's great for all the reasons that you've heard, but we find it even more effective if we combine it with some scalable data science tools. And so I mentioned here Spark on EMR and SageMaker, and that's been really successful for us. What we're looking at in the future is to really stay in touch what's going on in the, what I call here the machine learning, deep learning periphery. And that's all the tools that are being built by companies like Uber and Google, like TensorFlow Extended, to really make that data input pipeline, data validation, schema checking at scale a lot easier. And with that, I will dive into my case study, which is basically yield prediction, crop yield prediction based on satellite images. And I'll start with the observation of the amount of data that we're gathering. 5 years ago, in 2015, we had about 5 million acres in our data system. That may seem a lot, but it really isn't. And that's because there's so many soil types and there's so many weather scenarios that 5 million for 1 year is just really a small amount of the of all of the options that can happen, all of the different combinations that can happen. Fast forward to this year, we will have about 90 million, we project at the end of the year, 90 million acres of yield data. And so that's probably one of the world's biggest databases of crop yields. Note also this sort of stepwise format of this graph, and that's because for every field we get one data point per year, and there's only one harvest per year. And so that makes agriculture particularly unique, that we can't collect data usually, or data that matters in terms of revenue throughout the year. There's only one point in the year that we get that data. The other observation is that the amount of data that we're getting from satellites is also exploding. We are at this point being surrounded by about 5,000 satellites. This is just an artist's rendition. Obviously, it's not to scale the satellites versus the Earth, but it gives you a sense that it's crowded up there. About 40% of those 5,000 are still active. There's a lot of space junk. So that's about 2,000 active satellites, and of those 2,000, about 700 are observing the Earth. So at any point, at any location, at least in the US, for several points during the week, you can get a really nice high-resolution image of what's going on in that field. And often that's not just color, so not just RGB, but also near-infrared and other bands that are really important for photosynthesis, and that really give you a good idea of the amount of biomass that's growing in that area. And so the premise of this project then becomes, can we look at time series of fields of satellite image and maybe combine it with other layers such as weather, soil, or topography to in the end come up with yield? Usually we think of this problem in two scenarios. One scenario is hindcasting mode, where we have the data throughout the year and maybe the yield happened in the past, and we're trying to hindcast what that yield would have been. And this is great if a new user comes onto our platform and just says, this is my field, I'm located in this area, then we can at least have an idea of what the historical yields were in that field. And then there's also forecasting mode, which is a lot harder, obviously, where throughout the year, throughout the season, we're gathering the satellite data and we're trying to make a prediction for 3 months out. Now, nobody can predict the weather that far out, so that is a really hard problem that many users are working on. But at least we can get an idea of the variability and decrease the variability over time. The hardest part of this problem, of this project, is really the input data pipeline. It's quite complicated, and it's one that we had quite a number of iterations on. So we start with our data warehouse. In the end, we're running something in TensorFlow. That's basically the framework that we're using. And since in deep learning, most CNNs, most convolutional neural nets, need a fixed size of image as an input, we need to tile the satellite data into discrete units, and we need to be able to do that at scale. That's a great job for Spark, so that's something that we're doing inside of Spark. After the satellite image is basically tiled into little chips of maybe 500 by 500 pixels, we're joining that specific location with other data, and that could be management data. What type of seed did you plant on that field? It could be soil data. What soil types do you have? What is the organic matter content? What is the pH of your soil? As well as weather data. And so we create basically a nice package at that point. The next step is to be able to filter at scale also, where we want to exclude maybe fields that had high cloud coverage, or maybe fields that didn't pass some sort of data quality check. Then there's a transform step where we want to do some missing value imputation. We want to normalize with the average and the standard deviation that is relevant for that field. So we have to do some group bys and some summaries at that point. And then there's also some feature engineering that is involved. And then at the very end, we store the data again. We usually work with TF Records, which is TensorFlow's proprietary format. But we are more and more looking into and getting excited about a technology called Petastorm, which is an open source library done by Uber ATG, their autonomous vehicle division that lets TensorFlow train directly on Parquet. That's super exciting because we are a big Spark shop also, and so we can do all of the input pipeline transformations, joins, and tiles and filters on Spark, and then directly use the Parquet file in TensorFlow. So we don't have to mess around with an intermediate data format. Then in terms of training, let's talk a little bit maybe on the size of this problem. Like right now, I talked about 90 million acres. That represents about 1 million growers fields in the US for the past 5 years, and that's just corn. We're focusing at this point just on corn, mainly because it's ubiquitous and it's just where the biggest data is. On the fastest GPU, this type of model can probably process about 12 tiles, 12 examples per second. If we want to do 5 passes over all of our data, a single training job on the most expensive GPU on AWS would take us 20 days. Now, fast forward 5 years, suppose that we have even more data, we do more crops, more regions, we can easily get to 10 million fields, and that would mean that a single training job would take us 200 days. And so you can imagine that just doing single instance training no longer works. And that's why we're so heavily invested in distributed training and trying to understand really how to make distributed training as simple as possible for data scientists. We don't want them to have to run scripts or to set up a cluster, or we don't want them to really mess around with the installation of CUDA or any other libraries. And that's where, for us, SageMaker has been super successful. It has that ability to do one-click deployments. The cluster is automatically started when a training job is started. It's also automatically torn down when either the model ends or there is an exception. And so that's also something that makes it a little bit easier to manage. And so the paradigm that we have is our user works from within Domino, runs all the experiments within Domino. They can share their results within Domino. But just for training, that's where we're going to move to the more expensive instances where we want to make them work on crunching the numbers. So I'll end with reiterating the lessons that we learned for the case study. This case study could not have been successful without really having a data engineer and a model practitioner and a machine learning engineer in the same room, doing stand-ups together, learning from each other, and making the project effective. And the second lesson is, this is a great example of how you can use Spark from within Domino together with SageMaker to really use the best of all the tools that are out there to do a highly effective and scalable training. And with that, I can open the floor for any questions, or we can also move to the Tonga room and talk about questions there.
Great talk. I've got a billion questions, so I won't ask them all. I guess one question that's maybe just a curiosity, have you looked into GPU databases at all? And do you think they have a future? Because you have very structured data after it's processed. Have you considered GPU databases, and do you think there's a future for that in deep learning?
Yeah, we have not considered it. Yeah. I don't even know. I've not even heard of GPU databases. Yeah. I can imagine what they are, right. But yeah.
Cool. And the other, this isn't a question, just an observation. You might be the only company I've heard of that probably has old school stats like design of experiments, split plot designs, all the way up through the entire life cycle of machine learning through deep learning. So it seems like a pretty cool use case.
Yeah, and obviously as part of being in agriculture, there's a lot of, it's a very interesting industry in the sense that it's fairly risk averse. And even within the organization, people are generally risk averse, and it's creating a very interesting dynamic because I do believe that we're at the cusp of a revolution where we're getting so much data now that we're getting at least a crack at solving the yield equation. And so it's going to be definitely interesting times ahead there.
I have one just kind of like echoing Chad's talk, but how do you manage with like climate change and things like that as part of your models? Is that just another sort of stack or layer?
Yeah, climate change still happens at a time scale that is maybe more years to decades. And so as we get more and more data, we'll probably want to downgrade data that's 5 years old and maybe put more emphasis on more recent data for that reason. But especially if we look at long historical time series of yields like the ones that USDA are curating, that's definitely something that you have to do. If you're using that data to look at current trends, your conclusions will be very biased. The other thing that I want to mention is that the pace of agricultural innovation is still quite huge. So we're still increasing our crop yields by maybe on average 3 to 4 bushels per year. And so if you use in your data, in your model, yields that are maybe 10 years old, that technology from 10 years ago is not representative of what's going on today. So climate change and also agricultural technology are two reasons why, yeah, we have to really watch out with using older data for fitting models. Yeah.
Okay, thank you, Stephen.